Lighting in a game is incredibly important. The difference between a game with no lighting and good lighting is night and day. And I don't mean literally. When I initially planned my 3D mining exploration game Magical Mining coming soon to an app store near you, please follow my social medias for updates, I knew I'd need the obvious. Cave generation, player movement, loot systems, etc. What I didn't anticipate was that I'd need to build my own lighting from the ground up because Unity systems just didn't fit my needs. I bet you're wondering, what are those Unity systems? Well, I'm glad you asked. Games traditionally use two methods of lighting, baked and real-time. Baking is where you calculate the lighting outside of runtime. The lighting is stored as a light map texture, and then the material reads this to apply the lighting to the texture. This saves massively on GPU performance, as all the calculations are done before running the game, but it does need more memory to store all the light maps. It also takes ages to bake, and you gotta rebake every time you move something, so it can get quite tedious. This also only works for objects that don't move. In more complex situations where the environment changes, runtime lighting may make more sense. This does the calculations every frame, meaning the lighting will automatically change for you. Games will often use a mix of the two though to allow for both benefits, like a flashlight in a dark environment, or buildings where the light inside is baked, but the outside environment is done at runtime using the sunlight. There's also light probes which you can use, which I'll link a good Unity video which goes into detail, but it's basically just a way of baking light for moving objects. Anyways, despite all this, since Magical Mining plays in a procedurally generated environment, each tile is created at runtime, so traditional Unity light baking and light probes aren't really an option. This leaves runtime lighting, which works alright. The issue was that it can be difficult to get good performance with this, especially on low-end devices. When I tested real-time lighting for my game, benchmarks showed that I could get stable FPS on my phone, but it was still quadrupling the length of the rendering loop, which is far from ideal and would likely cause problems later as they added more graphic features. It also heated my phone so much after just a few minutes of playing, I probably could have cooked an egg on it. Additionally, it faced a problem with the total number of lights that can hit the surface. The universal render pipeline only allows for 4 lights to hit an object at once. This can be increased to 8, but it's not recommended for performance reasons. This wouldn't have worked with the floor as it was just one big tile map. I would either have to limit the number of lights on the scene to 4, or split the floor up into lots of small tile maps, but that would have been a massive pain in the arse. I needed alternatives. There was a voxel-based lighting system called SEGI which seemed promising, but hadn't been updated in years and had a severe lack of documentation, so relying on it was a bit of a risk. There was also a paid asset I found which looked promising, but I'm kind of on a budget here. Eventually I decided to try my hand at a custom system. I thought this would be fairly feasible considering my game's simplicity and the fact it's built out of voxels. I found this post outlining how the lighting works in this decade-old game called Blokworld that doesn't seem to exist anywhere outside of this forum. This post describes a system very similar to Minecraft. It essentially performs a variant of a flood fill, which I talked about in my last video, to calculate how much light should fill each block. In Minecraft it works similarly, and each block is assigned a light level from 0 to 15. The proposed solution had a fair amount of complexity, but a lot of it could be simplified due to the nature of my game. Firstly, there was no verticality in my levels. This meant I'd only need to account for horizontal distance from a light source. Secondly, the environment wouldn't be changing dynamically. This meant the system didn't need to be designed and optimized around being run multiple times. I just need to run it once at the start, which made my life a lot easier. I was confident that I'd be able to pull this off, although probably too confident, but I'll get to that later. So I had the idea, it was time to get to work. First, I needed to actually place the torches and calculate their light levels. This was fairly easy to do, as I could use the previously outlined flood fill solution. It starts at the light source, then for every connected tile it moves to that, and set the tile's light level to be 1 less than the previous tile. It only does this if the new brightness is higher than the previous one, to prevent overwriting it. Repeat this until the light level reaches 0. With this system, I could actually calculate where to place light sources. Since the level generation already stored the edge tiles, I just went through them all, and if the light level was too low, it would place another torch. The result is a cave where no areas can get dark. Calculating the light level was easy enough, but next was the hard part, and actually representing that light. Well, making it look good would be hard at least. I could have settled for visuals similar to old school Minecraft, where the lighting for each voxel is very harsh. But this doesn't feel particularly polished, and I knew I could do better. I wanted a system more like modern Minecraft smooth lighting, where the lighting is blended across the tile. I struggled coming up with a good way to pass information into the shader for each tile to do this. After some brainstorming, the idea I settled on was passing the vector 4, which contains 4 values. These 4 values would be the light level of the adjacent tiles around it. That way, I could use each value to blend across all 4 corners. This was surprisingly difficult to get working across the whole model, but the result worked nicely. There was no time to celebrate though, as I quickly realised this only worked on 1x1 objects, and since the floor would usually be around 75 by 75, this wouldn't work at all. The floor was actually just an invisible plane with a tile map on top of it, so if I wanted to do this lighting, I'd have to ditch that idea. Since you can't apply different materials to different tiles, I guess I could split the floor into individual tiles, but that's a lot of unnecessary objects and planes, and it would slow down generation time a lot. There didn't seem to really be a viable solution to this. so I had to ditch a lot of what I'd done so far. Now at this point I was completely screwed, and I was losing all hope. The deadline for the demo was quickly coming up, so I really needed a solution quickly, but I really didn't know how. When you're days into something, completely stumped, and not even ChatGPT can help you out, what can you do? Except take a break, and go to Costco and get a $1.50 hot dog, which is what I did. It was pretty nice. Lucky for me, once I'd returned, this great value hot dog had given me a new perspective on the problem. What I needed to do was have a separate shader for the floor, and somehow pass the light levels of the entire cave into that shader. Shaders don't support lists, so I couldn't just pass a big list of all the light values. How else could I pass a dynamically sized list of data? Maybe I could store the light values of each tile in the texture, with each pixel representing a tile? That works. And then I just read the value in that texture to oh. And then I realised that this was just light baking. The concept that I initially dismissed at the start, I'd ended up just coming up with my own solution for. A solution which fit the fact my game was made out of voxels. Anyway, this worked great, and was generating some pretty cool results. It was quite easy to sample the texture in the shader. The only issue was calculating the correct UV position of the floor, to sample the correct part of the texture. It ended up using the world position, and some math involving the overall room size. The result worked perfectly though. Here's the initial result with the light levels sampled directly onto the floor, and then here's the version where it's blended against the floor texture. The beauty of this method also meant that the walls and tiles could use the same system. They could just sample the light map, so there's no need for that overcomplicated system I created before. It also meant I didn't need to pass anything into the material. I could just set the light map and the room size as a global variable, and it's also way better for performance, as all the objects didn't need their own material instance. Soon enough, I'd end up with an actual functional lighting system, and it was beautiful. This method ended up doing many things for me at once. One great benefit was that since the light map was stored as a texture, I could utilise the filter modes that Unity provides to blur the texture. This meant it automatically applied smooth lighting, without needing to do any blending in the shader. It also had this really cool side effect where the walls fade out to black along the edges. This took a massive weight off my shoulders because I knew I wanted to implement something like that, to make the caves way more immersive, but I kinda had no idea how to do so. This did it for me accidentally. It's actually crazy how much just some simple lighting really elevates the visuals for the game. It turned from ugly dev art into something actually presentable. Like I said at the start, I initially had no idea the lighting for the game would need so much work, since I usually stick to 2D or just basic directional light. The topics in this video were pretty surface level, so there's a lot more to learn. I'll link a really interesting video below about the mobile game Elder Scrolls Blades. It goes over their custom lighting solution for procedurally generated dungeons, as well as just general optimizations. It's pretty cool. I hope you enjoyed the video. If you're interested in the game I'm working on, I've linked all the info below. I'd really appreciate any support. Recently, I also had the chance to showcase a demo at the VentureFest South exhibition. With that, I released the demo that I made for the event onto itch.io, so feel free to check it out and give it a play. It would be cool to get some feedback. Anyways, thanks for watching, see you next time.